Okay, this is unit number 5, work and kinetic energy, and I'm going to start you out at example number 2. We're on page 3. Now, if my memory serves me right, see, 4th hour, I think we stopped right at the beginning of example number 2, and 6th hour, I think we got through some of example number 2. So, 4th hour, folks, I'm going to start right here. 6th hour, folks, we worked it down a little bit further. So 6th hour, folks, if you just want to listen to this, that's fine. Or if you want to fast forward to the rest of it, that's perfectly fine too, however you want to deal with it. But I'm going to start right here. Alright, it says draw a free body diagram of someone dragging a 60 kilogram box 10 meters with a force of 200 newtons at an angle of 60 degrees with the floor when friction is 40 newtons. Label all forces. Alright, so we know we've got weight, and we know we've got normal force. Alright, and then it looks like we've got this 200 force is drug at an angle like this. So that's 200, but we're going to call that, we're going to give it a nickname of FA. It's the applied force. Let me zoom in on this so you can kind of see what's going on with it. Alright, and it also notes that we've got friction. Where's it at? This 40 newtons is friction. So we know friction is going to oppose motion, so that'll be 40 newtons, and that'll be F of F. And then it travels, I think it travels 10 meters. Alright, so there it is, and we can kind of run through it here. Alright, so it says calculate the work done by the person on the box. Alright, so there's two ways of doing it. We're going to use the work equation from the other day. So work is going to be F dot D. And remember that when we deal with F dot D, that's the same thing as FD cosine theta. Don't start here. I really want you to get used to writing F dot D and getting used to that notation. That'll be important a little later on. So I'm trying, even though it might seem like a lot of work right now, trying to develop some good skills in you as well. All right, we want the work done by the person. So if we want the work done by the person, we have to, this is the key here, we have to use the force exerted by the person. So the work done by the person and the force done, those have to go together. If you don't have those matched up, it's not going to work for you. So the next step is just to plug the numbers in. So the force exerted by the person is 200 newtons. That's this guy. That's the applied force. So we'll say 200 newtons. Distance is how far it travels. And then this angle, now this is where it gets tough. The angle is the angle between this force and this movement. That's the way you want to think about it. This force and this movement. Which way is this force? I'll use pencils to kind of illustrate this. It's going that way. Alright? And then the D is this way. And so that's the angle that we're looking for. And they tell us in the problem that that's going to be 60 degrees. So we'll go ahead and punch in 60 degrees. And if we try that out, so 200 times 10 times cosine is 60. Close that off, and we get 1,000 joules. And so we could say 1,000 Newton meters, because that's what we've got right here. Okay, and then we also have 1,000 joules, because we know a joule is a Newton meter. All right, now that's the first way of doing it. We're going to do the second way, and the second way, instead of focusing on this force right here, we're going to focus on its component. So we're going to say the work done is equal to F dot D. Work done is F D cosine theta. This is the work done by the person, so this is the force done by the person. Now, I know that when, let's see, now this force here has an x, let's see, a y component and x component, but because this component is perpendicular to the motion, those are perpendicular right here, because these are perpendicular, this part here does no work. And if it doesn't do any work, I don't need to worry about it. So in this particular way, I'm going to just focus on this component, which is really this guy here. It's the x component of the force exerted by the person, or the applied force. Maybe I could put a P, the force exerted by the person. Maybe that'll help out a little bit there. Maybe it would help if I write so you can read as well. Alright, so here it is. Work done by the person is equal to. Alright, now what is this? That's the side that's adjacent. And so the side that's adjacent is going to be cosine. So this guy right here is really h cosine theta, which is really the force exerted by the person cosine theta. Yeah, we'll say it that way. Now I know a lot of you guys, I saw this on the test. You plug right here. You plug 200 newtons cosine of I think it's 60 degrees, and you got a number, and you plug that in. I really want you to resist doing that. Just go ahead and plug in force exerted by the person cosine of theta, distance, and then cosine of theta. And notice I got two thetas, so these are different. Actually, these are different angles. I might maybe put theta 1 and theta 2 in there just so I can kind of see the difference between the two of them. Alright, and let's plug numbers in. So work done by the person is equal to the force exerted by the person. That's the that's the 200. Then the cosine of, now that's this angle here. That's theta, that's going to be 60 degrees. Times the distance that it travels, 10 meters. And then cosine of, now this theta is the angle between this force and this movement. It's always the angle between the force and the movement. Remember over here? This theta was the angle between these two guys. Same thing. This theta is the angle between the force and the motion. Well, what's the force? It would be, let me correct that a little bit. It's the angle between this whole force and the distance. That would be a better way of saying that. Could have been misleading the way I had it earlier. So this together, the FP cosine theta is this. I'll write that here. I'll do FP cosine theta. So theta is the angle between this guy and this motion. Well, I'll use my pencils. That's the direction of the force, and that's the direction of the movement. Those two are parallel. The angle between those two is 0. So let me go ahead and plug that up here. So WP, and then I'll go ahead and see if I can plug this stuff in. So I've got 200 cosine 60. I'm going to go ahead and just figure that out first. That's 100. And then I'll go ahead and multiply times 10, and then multiply times cosine is 0. And I get 1,000. And I should get 1,000 because that's what I had in the previous part, method number 1. So that'll be 1,000 joules. So you could do it one way or the other. Just do it this way, but I wanted to do it the other way just so you can kind of see another way of doing it as we went through it. All right, letter B. This one, now this one up here, this is the work done by the person. Now we want the work done by gravity. So we'll still use the equation. Work is F dot D. So work is F D cosine theta. Since we want the work done by gravity, we want the gravity here, and we want the force of gravity. As soon as we say force of gravity, remember that's weight, which is equal to mg. So I can go, let's see, I can go mg d cosine theta. The mass of the box is 60 kilograms. That's from above. The acceleration of gravity, we'll just say 10, make it easy. And the distance is going to be 10 meters. And then cosine of. Now we need to get the angle between this. Remember, this is the angle between this force and this movement. Well, that's the weight. So the weight is straight down, and the motion is straight across, and those two are perpendicular to one another. So that'll be 90 degrees. And you'll find out real quick that 90, cosine of 90 is 0. So the whole thing becomes 0 joules. So gravity does no work on the box. That's the way you want to think about it. Gravity does no work on the box. All right, the next one, it says work done by the ground on the box. So F dot D, I know that sounds like a lot of extra work there, but it'll pay off later. All right, so we want the work done by the ground. Well, the work done by the ground is really the normal force pushing up on the object. Well, let's just kind of see if we can shorten this up a little bit. So this is FND. I'm just going to plug the number in for cosine because I know what's going to happen. The normal force is up, the motion's to the right, and those are at 90 degrees. So the angle is 90 degrees. Come on, computer. Alright, so then cosine 90 is going to be 0. So this is 0 joules. So the ground does no work on the box. 0. Last one's friction. I'll do friction up here. I'll kind of give myself a little room. So work done is F dot D. This is going to be FD cosine theta. This is the work done by friction. This is friction. Well, what's friction? I think if I go back to my diagram, it was 40 newtons up here. So I'll go 40 newtons. Now, I'll say this. We don't use, even though this is to the left, we don't use the sign of negative. Because as soon as I go from this step to this step, this was a vector and this is not a vector. And since it's not a vector, I'm not concerned about the direction. If I'm not concerned about the direction, I don't have to plug in the negative. And that's real important that I not plug it in there. The distance is 10 meters. Cosine of. Now let's check this out. The friction force is to the left and the movement's to the right. So the angle between those, okay, you could think of as 180 degrees. So I'm going to plug in 180. Okay, you're going to find out if you plug this in, 180 degrees is going to be negative 1. So I've got 40 times 10 times negative 1, that's negative 400 joules. So the work done by friction is negative 400 joules. The work done by the ground is 0. The work done by gravity is 0. And the work done by the person is 100 joules. All right, let's flip the page and see what we can come up with on the next page. Alright, so based upon our discussion, does the sign of work indicate direction? And that's no. And the reason for that is work is a scalar. Okay, it's not a vector, so it doesn't indicate direction. So if so, work must be a scalar quantity. Now, that doesn't mean that work can't be positive or it can't be negative. It just, the sign of work doesn't indicate which way. So work is positive. It can be positive. And so work is positive when the force or a component of the force acts in the same direction as the displacement. If I flip this over and I go back to the previous page, notice that in the first case, the work done by the person is positive because this was to the right and this is to the right. Now you say, well, that's not to the right, but there's a component of that force that's to the right. And when those two are in the same direction, the work done is positive. Okay, the next one. Positive work indicates that the work done by the force, if the force were working alone, causes the object to speed up. Therefore, the overall kinetic energy of the object increases. So that makes sense. If it speeds up, it's going to have more kinetic energy. So let's go flip back over here. So doesn't just the act of this guy dragging this box cause the box to speed up? I mean, assuming there was no friction. So if that force were just acting alone, just the sheer act of pulling on the box is going to cause it to speed up. That's why work is positive. All right, work can also be negative. And we'll get to that in just a second. Since the force caused the energy level to increase, more kinetic energy, the work done by the force is classified as endothermic. You may have heard of that word in chemistry. So endothermic means energy is going into the system, into the box. All right, as we said also, work can be negative. Work is negative when the force or a component of the force acts in the opposite direction of the displacement. So did that happen in the previous page? Yeah, it did. Right down here, friction. Friction was acting to the left, and the motion was to the right, and that was in opposite directions. So friction came out to be a negative work. It was negative because the force and the motion were in the opposite direction. So negative work indicates that the work done by the force, if the force were working alone, that's important, causes the object not to speed up in this case, but to slow down. So if the object was already in motion, and friction was acting on it, and no other forces, the friction would cause it to slow down. That's negative work. Therefore, the overall kinetic energy, the overall energy of the object it'll decrease. We're slowing down. We're losing kinetic energy. And this time, instead of being endothermic, we're losing energy. So since the force causes the energy level to decrease, the work done by the force is classified as exothermic. There it is. Alright, so we're going to take this same example and we're just going to build on it as we go. So letter E says calculate the net work done in a box. Well, if I come back over here, I had four forces. Okay, I had the friction, I had the normal, I had the weight, and I had the force exerted by the person. I need to figure out the work done by each one of those and add them together. That would be the net work. Well, two of these, we just did it right here. Two of those didn't do work. I only had work done by the person, which was 1,000 joules, and the friction, which was negative 400 joules. So it's going to be, if I can show it here, 1,000 joules done by the person plus 0 joules done by the normal plus 0 joules done by the weight, or you could say gravity, plus a negative 400 joules done by friction. And that will give us a total of 600 joules. So the net force, or I'm sorry, the net work is 600 joules. You just add them all up. So now think about this. If 1,000 joules makes it speed up and 400 joules makes it slow down, then the speeding up is more than the slowing down. So the overall net effect of speeding up and slowing down is going to be speeding up. So based upon your answer, is the object speeding up or slowing down? And it'll be speeding up. And speeding up because the net work was positive. And that's important that the net work was positive. Alright, the next one is we want to calculate the net force acting on the box. Net force. Alright, well, let's kind of just flip it over real quick and just look at the forces that I have here. Net force. Well, let's see. Now, the object's going to the right. And if the object's going to the right, there's no acceleration in the y direction. If there's no acceleration in the y direction, all my forces in the y direction cancel out. So I really don't have to concern myself about the forces in the y direction because they all cancel out because I have no net force in the y direction because they're all balanced. There's no acceleration. However, I do have forces in the x direction. I've got the force of friction, and I have this component of the person. I'm going to draw those over here so I don't have to constantly flip back and forth. So I've got friction this way, and I think friction was 40 newtons. And I got the applied force, the force exerted by the person, however you want to use that, is 200 newtons, and I think this was an angle of 600 degrees, or 60 degrees. So to find the net force, I need to find this component here. So I'm going to go H cosine, because it's next to, this would be the sine part. The H is the hypotenuse, that would be 200 newtons. Cosine is 60 degrees. So 200 cosine is 60, and that's 100. And that'll be 100 newtons because it's force. So if I figure out my net force, it's 0 in the y direction because everything cancels out. We talked about that just a moment ago. And then in the x direction, it's negative 400 negative 40, and then positive 100 newtons. And then in this case, that gives you 60 newtons. It's positive. It's positive because the net there's more to the right than there is to the left. Some of you may be thinking, well, why did you keep the positive here and then we dropped it when we did the work? Well, remember, force is a vector, and vectors need direction. Work is not. Sorry. Work is not a vector. It's a scalar, and we don't need direction on it. All right, so there it is. Let's go to the letter G. I'm going to get you all the way through K, and then we'll be done. And then we'll pick up from there tomorrow. All right, so calculate the net work on the box from the net force. Okay, so we want the net work from the net force. So let's write the work equation. And then it's FD cosine theta. All right, now you can grab a sharper pencil. There you go. All right, so the net work is going to be, well, that one broke. It's not going to do me any good. If I want the net work, I need the net here, and I need to use the net force here. So I have to use both of them. Those always go together. Remember that? So if I want the net work, I have to use the net force. And the net force, I figured out in the previous example. Okay, what was that? That was letter F, and that was 60 newtons times the distance, which was 10 meters, and then the cosine of the angle. So let's think about that angle real quick. This is letter F, the one we just did. The net force is to the right. That's this way. And if the movement's this way, what's the angle between those two? The angle is going to be 0. So on this one, it's going to be 0 degrees. And cosine of 0, you'll find out, is 1. So 60 times 10 times 1 is 600 joules. That's the net work. Now, how does this net work? You calculate in part E, compare the net work you calculated in part G. Well, E is right here, 600. Okay, 600 joules and 600 joules. And we got 600 joules in both cases. And that's what we should have done. Should give you the same thing. So we'll go same right there. All right. 4 more questions. Next one's long, and then the last 2 are easy. Here it is. If the object started from rest, so we're starting from rest, which should be a tip-off, because if we start from rest, all of a sudden I'm telling you that the initial velocity is 0. If the initial velocity is 0, that's a tip-off that we're going to be using big 3. How fast is it traveling after the first 10 meters of pulling? So let's just go ahead and write down what we have, and then we'll see what we've got. So we've got D. We know we're going to be using the big 3. D, VO, VF, A, and T. All right. The distance is 10 meters. We know that. Initial velocity is 0. We don't know this. We want to know it, and we don't know the acceleration. It's not in free fall, so it's not going to be 10. And then the time we obviously don't know. So there's things that we don't know. So we need to get we need the acceleration. And if you remember from last chapter, a lot of times to get the acceleration, we'll have to go to Newton's second law and use Newton's second law to get the acceleration. And that's what we're going to do. So we're going to sum up all the forces in the x direction. We had 2 of them. We had the force of friction and the x component of the person pulling it, and then max, we want this to use here. So ax is equal to negative f of f plus f of px over m. Now, actually, I have enough information. I've figured out all this information already. They gave me this. This was 40 newtons. The force exerted by the person, where did I figure that out? That was, what letter was that? Okay, that was, I think in letter F. I had to figure that out kind of quickly. And I think that was 100 newtons. So if you stop the tape, look back to letter F, you'll find out where we did that. And then the mass, they tell me. And the mass, they told me earlier, I think was a total of 60 kilograms. And so I think the 60 kilograms came from like the first part of the problem or something like that. So negative 40 and 100 gives you 60 newtons over 60 kilograms, which is 1 meter per second squared. And there it is. Alright, and then the last part is to find the speed, and we can get the speed from Vf equals Vo plus At. I got the wrong equation. I don't know time. Try that again. So we get Vf squared equals Vo squared plus 2Ad. Initial velocity is 0. Since it's moving to the right, I want to choose the positive part. Acceleration is 1 meter per second squared. The distance is going to be 10 meters. So Vf is equal to, let's see if I can plug that into my calculator. You get an answer, square root 2 times 1 times 10, we'll say 5. And there's the final speed. Alright, we're doing great. Three last questions, but these will be a little faster. Alright, how long does it take the person to drag the box 10 meters? Well, where are we going to get how long? How long is going to come from the big 3? And it's the equation actually I tried to use earlier. It didn't work. So it's a Vf equals Vo plus At. So time then will equal, let's see, Vf over A, and Vf equals 4.5. Acceleration is 1 meter per second squared. So it'll take 4.5 seconds. Alright, and then there's the next question, letter J. If the object is dragged at a constant velocity, that's the important part here. So this is a little bit different. In letter H and I, it was accelerating, but I'm changing the problem a little bit. Let's say we drag it at a constant velocity. Alright, if we have constant velocity, that implies that the acceleration is equal to 0. It's not speeding up, it's not slowing down, it's not turning. If there's no acceleration, all the forces are balanced. Put that down. Balanced forces. If the forces are balanced, then the net force has to equal 0, and that's what it's asking right here. So the net force acting on the object is 0. Now we're going to use that to answer letter K. If the forces are balanced, then what's the net work? Well, it's got to be 0 joules, because if it's 0, that means energy going in to cause it to speed up is going to be totally canceled out by the energy coming out that's going to cause it to slow down. All the positive work is going to be canceled out by all the negative work. And so there's a net 0 work done, which means that the energies entering the objects and the energies exiting the object cancel out. There's our video. We'll see you tomorrow.